Fabulous, thank you. Everybody hear me okay? Good deal. I just leaned down and pulled on the little cord from the microphone. I was afraid I broke the whole thing. So that's absolutely right. I'm going to talk about basically the last 4 years of our experience from having written a fairly large system in Ruby and then deciding which parts of it should and should not be. And I'm going to talk about the pros and cons, and then you'll probably discover mistakes we made along the way as well, undoubtedly. Most of these things that you discover are actually after you make a mistake, right? First, very, very quickly, so this is me. I was one of the early guys on Amazon EC2. I actually staffed the team for the first 2 years in Cape Town, South Africa. So fun, bumpy road. How many of you have used EC2? Okay, so there's a whole series of things you can blame me for after the talk, because it happens every time. After that, I was that guy. Did something remarkably like EC2 on the inside of Microsoft. And then finally, for the last nearly 4 years now, I've been working at Opscode. I'm the CTO there. This was us at Velocity. How many of you have used Chef, which is Opscode's product? Wow, I wasn't sure what to expect coming over to this conference. How many of you are Rubyists? Ah, even better. How many Erlang programmers? Okay, there we go. That hits the expectation. This is going to be a lot of fun then. All right, so very quickly, I'm going to talk about what our product is to set the context for how we made our decisions and how we made our mistakes. Talk about it both from who uses it, but then from an implementer's perspective, again, why it is we made choices. Why we chose Ruby, why we chose Erlang, and then how we ported our server side from Ruby to Erlang and what we got out of doing it. By the way, we have a very, very large open source component to what we do. So the server part that I'm talking about, the port that we did from Ruby to Erlang, is basically just hitting the shelves now. We've had preview builds for a while, but it's all available on GitHub. I can send out links to it. We're sending out release candidates for the entire package this week. So you can go and take a look at exactly what I said. First of all, so Chef is for systems administrators or for systems architects doing deployment, doing infrastructure automation. So you can think about it in the same evolutionary family as CF Engine or Puppet, and to some extent tools that have gone before like BladeLogic or Opsware. So everything from you have a bit of an operating system on your machine and you want to go all the way up to deployed applications, deployed monitoring, state and asset tracking of those things on the server. So this is a great quote. It's like a little sysadmin robot. That's exactly what it is. It produces the same actions repeatedly over and over again. You can ask it to work all night long. It's built up of a number of different conceptual pieces. There's a code repository. Our mantra is infrastructure as code. So the notion is, from a development point of view, you should be able to treat all the things that define your infrastructure as if they were also code. So you check in your source code. You also check in the description of your infrastructure, which is in fact executable. So you can version it the same way. You can push it down the same pipelines as you do everything else. And it's really a great way for developers and systems administrators to reach a common ground, to talk about the same thing. So you often hear us wrapped up in the entire DevOps discussion and DevOps argument. Because of that, we are actually a bridge tool between. We've got a server-side component, which is basically a publishing platform. You send us these descriptions of your infrastructure so that all of your infrastructure can then fetch those after the fact. So we need to be fairly scalable in that you publish something once perhaps, but you fetch it across every server in your infrastructure and multiple times. So it could be thousands of machines and it could be quite often. And then we've also got a client-side piece, which is, there are actually two bits of it. There's the piece that executes on every server under management, and then there's sort of an administrator's command line tool. And at the end of the day, they're both just consumers of the server API. And that's another thing that we hammer on over and over again. We try to put very little policy in the API itself. There's this separation. Everything can call the API, everything can get the same results. So our client that we write would be no different than a client that you might write in Java or in Perl or in something else. Because at the end of the day, we want as many folks across the development landscape to be able to consume these tools. We've got a piece that we call data bags, where basically this is where you put unique and descriptive data of your infrastructure. Again, being a publishing platform, that's another thing where you might save it once and fetch it many times, or it's hard for us to tell what the symmetry is. You may be reading and writing both quite often. So it's an interesting use case. We've got recipes and cookbooks, and I'll talk in depth about exactly how those function later. And then roles and run lists, which are ways to compose your infrastructure where you can talk about them at a slightly higher level. Okay, so this is a recipe. And if you were here for the previous talk, there was a bit of a discussion about when you should create a domain-specific language and what it actually does. On the client side, we are very much about a domain-specific language, and we've got some fairly serious reasons for doing it. This is a recipe. Recipes are lists of resources, and they're evaluated in order. The in order part matters, and we can talk about that later. That's actually the big fight in the convergent infrastructure and infrastructure automation academic world. It's all about order, and it's all about convergence. So these, if you look at, let's see if I can make fancy tool work. Hey, there we go. Each of these sections is fairly self-descriptive. We talk about this as basically being the Holy Trinity. You have packages. What do you do with packages? You install them. Quite often those packages that you've installed are services. See that down here? And services have actions. You start them, you stop them, you might ask them for status. The other one here, templates or files, you quite often have configuration that travels along with these, and that configuration is typically data-driven. So we make it very easy for you to create a template that you then just render dynamic values into. So very powerful in that you can write a recipe once, you parameterize that, and you're going to send it out to every one of the machines that needs to execute it, driven by the data that's specific to that machine. So it's the usual thing, do the work once, have everything else work for you. And this is the sort of cornerstone to our DSL. And I'll talk a bit later about exactly why it's shaped the way it is and how we built it. This is pretty small crowd. We can be interactive. Feel free to stop me and ask questions or heckle. I figured that the last talk in here got a little contentious at the end. I'd like to spread contentious across the entire talk. We're on video after all. It's not like I'm escaping. So resources. Resources are those stanzas that you saw in the recipe. Resources have types. Like I said, packages, templates. When you look at a resource, it's the first thing you see. We want this to be easily consumed by systems administrators who don't like the notion of learning, yet again, another configuration language or another programming language. So our main plan here is to not shove a bunch of new concepts in your face. Domain-specific languages should be about your domain, right? So these have a type. They have a name. So a particular service, it could be Apache 2 or it could be Microsoft SQL Server. The name should be descriptive of what it does, right? Has parameters, because as I said, these things are all data-driven. And then we take actions to place the resource from the current state that it's in to the desired state. And the desired state is what's reflected in the recipe. So here, we also attempt to model these things in an item-potent fashion. We shouldn't take an action twice if it's not necessary. And if we do take that action, it should result in the same outcome. So what you should have is something that's very, very predictable, right? So in this first case, package Apache 2, the action is install. And actually, you could leave that out. The default is install, right? The second part of this, if you look at the template declaration here, and sorry for the wrapping. It's actually a little easier to read if it's not wrapped. It's exactly what you would expect. Well, what's the source of this? Apache2.conf. You know that's a thing that Apache is going to need to run, and you know that you edit it, right? That for sites enabled and all the other things. We happen to use ERB, which is basically a Ruby renderer. So these things, the configuration files, the templates, are written with parameterized little blocks of Ruby inside them. So what we do is we copy these out, and then we basically run Ruby over the top of it. So fairly easy to see what we're doing. But like any other file on your file system, it's got an owner, it's got a group, it's got a mode. And what are we going to do with this thing? We're going to create it on the file system if it doesn't exist. We also, even though it's not shown here, we have item potency stanzas, little things that you can do to these resources to say only if a particular condition exists or not if a particular condition exists. So you can make these things very item potent. If you need to check something about the system and say, I'd always take these actions unless I find the system in a particular state, you can tell us that right there in the resource. Make sense so far? So I sort of harped on what does it look like from the consumer side, why we would do this for a systems administrator from an implementer standpoint. So we've got two fairly different pieces. We've got a set of client-side tools, which are most often run from the command line. There's the client, the execution agent that runs on all the machines. And like I said, there's also an administrative form of that tool that some smaller number of folks run. Either way, 9 times out of 10, if somebody's running something against the Chef server, it's one of those two tools that we've written. The reason I frame it this way is I'll talk about the choices that we made in implementing those tools, radically different from what we do on the server. The second part of it is we've got this thing we, for lack of better terms, call a convergence engine. It's the piece that actually executes these recipes. It puts all the resources together from all the recipes you've specified, puts them in a particular order and dedupes them, and then executes all of them and tells you about the outcome. Because as you can imagine, quite often these actions fail for one reason or another. So you want to know exactly how they're executing, and you want to know what the outcomes are, and you want to be able to report back. So that convergence engine is the thing that takes all your input pieces of data and then actually runs it across your infrastructure. That's all done from the client side. From the server side, I'm sure you've heard the litany a dozen times now. We are a mostly stateless, RESTful, JSON-speaking API. I mean, you can write that on the back of the tin for almost every product here these days, right? It just feels like the right thing to do. I mentioned that we're a publishing platform in that you write to us the things you want executed, and then you fetch them from all of the clients. There's a little asymmetry most often in the number of times particular objects are written to us rather than read. There are other types of objects where we know there's almost one-to-one correspondence. Reading and writing happen equally as often, which is a little weird. Need to be scalable. We vend this product out in a number of flavors, but one of them we call Hosted Chef. That's us running a large scalable service on your behalf. And so you can imagine if our service is the thing that configures your infrastructure, you'd really hate it if we took downtime, right? Now, it's not like we're 100% reliable because nobody is, but we take it fairly seriously in that we try not to have scheduled maintenance windows. We try to do a number of changes live in the background when we do deploys, even going so far as doing very large data migrations while the engine is running. And I'm going to talk about one of those. And then, of course, fault tolerant, because you can't say scalable without saying fault tolerant, or I'd get heckled again. Client design goals, radically different from the server. So we want it to be easy to create tools. We want you to be able to consume our API. There are some bumps along the road. We have an interesting auth protocol, but other than that, anything can make a RESTful call and read JSON, right? We want to make this open to multiple languages. I wrote an API wrapper implementation for testing in Emacs Lisp that I execute from the inside of Emacs because I live in Emacs. And if you can write it in Emacs Lisp, you can write it in anything, really. Easy to hack on. Like I said, we've got a large open source contingent. It's fair to say that most of the interesting client-side code is actually written by others. And there's a huge, I keep saying asymmetry, but there's a huge asymmetry there. The client-side, very, very active community, hundreds of developers, 150 or so corporations have signed our license agreement to contribute. Lots of work goes on the client. So it needs to be easy to hack on, it needs to be easily understood in a language that's approachable by the masses. On our server side, almost nobody hacks on it. I think we have one external committer right now. So very, very different. It changes the choices that you're both constrained and allowed to make in the implementation. And then on the client side, nearly ubiquitous platform support. We want to be the thing that you use to converge your infrastructure regardless of whether or not you're on Linux or on Windows or Solaris. We support really old Solaris and we support Windows 2008 R2. And the span between them is really ugly, right? They don't look anything alike. The bedrock for that on the client side is a modern Ruby. If you can get modern Ruby on the system, chances are good we can make the rest of what we do actually work. So there's a choice. And then finally, the other thing that made the last talk contentious, metaprogramming and DSLs. I showed you an example of what we do on the client side. We are very, very much about that DSL and about continuing that and most likely introducing new dimensions to that DSL over time. And our choice of Ruby made that really straightforward. So really quickly, just to poke the bear, lots of languages to consider on the client side. We could have written this in something else. We want folks to be able to consume our API in other languages, but there are pros and cons, right? I could absolutely see, as a matter of fact, there was one implementation of the client in Java. You guys know JClouds? There's a, no. Cool. How many Java folks actually in the room? Okay, so there's a correspondence there. That makes sense. JClouds, wrapper in Java for many of the cloud APIs. There's also a wrapper in JClouds for Chef. So it's probably, second to our implementation, the most complete wrapper out there. So we could have done something on the JVM, but there are a number of reasons that's hard for us. One is, up until recently, there really wasn't a great language for doing DSL, easy metaprogramming and good DSL support, right? I'll talk a little bit more about that. Could have done it in Perl. Actually, there was a bit of an implementation at one point. When you think about it, Perl is quite approachable. It's attractive to systems administrators. And if you squint at it right, it's not so hard to fashion a DSL that's consumable. So actually, Perl was a neck-and-neck option at one point. Adam Jacob, one of our co-founders, is a real Perl bigot and actually started out writing it in Perl. And then sort of realized that, for better or for worse at that time, the Perl community was losing traction and the Ruby community was gaining traction, especially amongst developers. So, and then a series of other possibilities. This could be done in something like ML, where you get great typing and some interesting syntax. You could do it in Haskell for basically the same reasons. I know I'm going to get faulted for this, but I tend to think personally of Haskell as ML with futures. I like a lot of the same things about it. I've done ML and I haven't done much Haskell, so that's my mental mapping. Finally, if I had my first choice, it would be done in Lisp. And I know that's the one that actually starts the most fights. So I've hit most of this, I think. The goals of that DSL, translate your domain expertise to a language of implementation, right? The thing we don't want folks to do, you can imagine, systems administrators walk up to this, they look at a recipe, they go, oh, hey, it's a package and it says it installs. If I wrote that in Java, I would probably have something that says new package manager, factory, something or other, and then the guys would be asking, well, why new? What's the scope of the lifetime? What the hell is an object in its lifetime anyway? And you're off to the races. It would be kind of hard. So that backs up the second point. What do you want to do? You want to reduce that syntactic or that cognitive load on the consumer. You don't want them worrying about the rest of the stuff that's there. So in the last talk, there was some discussion about whether or not parentheses in Lisp add to cognitive load. I personally don't think so, but I get the notion there, right? If that's your consideration, if the folks that are using the tool, the first thing they run into is a thing they can't stare past, you've kind of already lost. Oh yes, yeah, the ubiquitous. I'd be that guy if I were a little braver. So the problems in choice, and this is an interesting separation between us actually and our nearest competitor, Puppet. Do you create an internal DSL or an external DSL? Everybody familiar with the differences? Okay, so the top level notion is internal DSL is actually the syntax of the implementing language. It's just typically the languages that are good for it allow you to permute it in such a way that you don't stare at a lot of syntax. I mean, we could talk about why parentheses at the end of the day aren't really syntax in Lisp, but anyway. External DSLs are ones where you write a lexer and parser or whatever in your implementing language, but the DSL language itself is something completely different. You at that point control the entire space. So that's the problem, right? How much of the original language do you carry along if it's an internal DSL? How much of the language do you implement if it's an external DSL? And how easy is it to understand and to teach? What constructs are necessary? So I've heard people talk about some of these external DSLs as, well, they're fine for what they do until I run into a thing they don't do, and then they don't do it. You're just sort of done. If you leave out a looping construct or a conditional construct in a domain-specific language, you're kind of done, right? How do you move forward? So this is my personal progression. I don't know how much of this makes sense to you folks, but I ran into SICP, and it, as some other people have said, it just sort of changed my world. The metacircular evaluator in, what is it, chapter 4 or chapter 6, that's the thing that made it all work for me in terms of why I would implement something in Scheme, why I would implement a language in a language, which led me to Lisp in small pieces, which is nothing but that over and over again. And then I realized I could do it on the cheap and other people would understand it. Because Ruby is sort of the love child of Smalltalk and Lisp, then appealing to Perl developers. I think that's fair. So this is my take on parentheses. In Lisp, you just don't see them after a while, right? It's like staring at the matrix. Anybody who's worked in Lisp for a while, the parentheses just sort of fall away. So I think I talked about all of this. Yeah, the heritage of Lisp and Smalltalk and things like that, the flexibility of the syntax, and that decision of whether or not you inherit types and structures. If you're doing an internal DSL, and you know that your implementing language has things like hash tables or whatever, do you simply cart those along into your DSL and allow your users to directly use them? Do you need to dumb down the construct or change it somehow? For us, we decided that you look at those resources, you can't tell those resources are Ruby for the most part until you do something like write one of the conditionals. If you say not if something, well, that thing you want to check, like most often it's you check the existence of a file out on the file system. So what you have to write is not if file : exist, ? And the name of the file. That looks like Ruby. And again, you're sort of off to the races. At that point, you need to learn at least enough Ruby to recognize it. And the external DSL, again, in for a penny, in for a pound, right? You're responsible for everything. There are some great tools out there that help you along, but man, I don't know how many of you spent time in Lex and Yak. Yeah, Antler's a fine tool. There's some, yeah, see, it's sort of funny. Everybody starts with one and graduates to the other if you're still doing it. But again, you're then responsible for the whole thing. I just loved this quote because it starts fights. This was Ola Bini when he was sort of looking at the same things. Realized that Java is not good enough language to implement applications. I'm not sure I'd agree with that for applications, but I think it's interesting that the JVM has sparked so much development in recent years, and that the languages that we're talking about at this conference are ones on the JVM that radically differ in their intent, right? I'm a big Clojure fan. Why? Because I love Lisp, and finally somebody rejuvenated it and brought it somewhere. Just to knock on the point for just a second. Yeah. Do I even need to say anything? This is actually, this is a snippet from what used to be Sun N1 server provisioning system. This is a piece of software that does something that's a lot like what Chef does. And if you stare at the XML pretty closely, the constructs look like our resources. It's really kind of crazy. You've got this deployment component, you've got the install steps, you've actually even got a little shell thing that executes at the bottom. So you can get to what I showed earlier, package template service, if you start here and factor down. So we actually did a large project where we took a bunch of N1 execution plans, turned them into Chef resources. So the mapping is very direct, but the syntactic load is hugely different. Erlang, I love me some Erlang. We've got Erlang all over the server. I would not try to tell systems administrators to write something that looks like that. I like it. I just don't think I can teach 6,000 guys who want to use Perl to do something so radically different. Perl, on the other hand, so this is why I said earlier, if you squint at it, that looks a lot like the other DSL I showed you, right? The resource, it's a file resource. That's the name of the file. And then it gets a little weird in that you've got this subroutine, I guess, that you have to do, and why am I shifting this stuff? But it's got an owner, and it's got an action, and if you don't think about it too hard, you could get there, especially if you're a sysadmin who already knows the language, right? This is my favorite. Yeah, figure out why, right? It's a resource, it's a file resource, it's got an owner, and it's got an action. That looks basically just like the Ruby version if you strip the parens off of it. Right? And you can even make it simpler if you really wanted to get to the point where you just called the resources by their type, file or template or whatever. I did it this way at the top just to show that everything's a resource of a specific type. All right, so that's pretty much it on the client side. Questions about that? Outright lies, fabrications? Server design goals, like I said, very, very different. When we started out, both the client and the server were written in Ruby. And pragmatically, you can see how you get there. We were a startup. The first implementation was basically one guy who then put it out into the world and let other people start working on it. Hugely approachable. One code base, one language, right? The design goals, though, when we built Hosted Chef, and we started, we put in some multi-tenancy, we put in some other isolation, and we started running this for hundreds of customers, doing thousands of convergences, we ran into some problems. So our goals, again, horizontally scalable. You want to be able to add new capacity to this service without, intertwining it with everything else. Highly concurrent, which means that mostly stateless request handling. You shouldn't have to think about which server handles the request, whether or not the request comes in twice, whether or not you have two concurrent requests that are talking about the same resources. And again, fault tolerant, because I have to put it on every slide. On the server side, same set of choices now in terms of languages, but the list of them, sort of balances differently when you go down. Don't need thousands and thousands of people to know how to hack on it. Like I said, the server side, not where our contributors come from. Startup time, kind of inconsequential. These are all long-running processes. Now suddenly the JVM starts looking a whole lot better, right? We could implement in almost any language that's good on the JVM. The one I left off this list, and I don't know why, was JRuby. Actually, JRuby was the highest contender for us when we first started the port. Why? Because we got lots of guys who know Ruby really well, and we want a thing that might be better at threading, that might be better with some of the memory concerns. Perl, no. ML, you're not going to get enough guys who know how to do it, and it's not exactly at the top of the list for web service implementations, right? Haskell may be coming along. We didn't have anybody that knew it well enough to say. And then, unless you're on the JVM, there's no scheme or Lisp that you can get enough people that know that is also battle hardened. You could pay thousands of dollars for Lisp works. I personally did in a past life. Or you could rely on something that's out there for free. But again, it's not like folks are building lots of frameworks today for it. So pragmatically, the one that's missing on the slide, though, is the one that we chose, which is Erlang. So we started with this thing that is Ruby running Merb. For folks in the know, Merb is a lot like Rails. Merb was an offshoot for a while that was then brought back in. So the request processing and routing stuff in Rails 3 is in fact Merb. So Merb, Ruby, Unicorn as a web server running behind Nginx as a reverse proxy. So again, stateless, scalable, all that stuff. We talked to CouchDB on the back end. We had a custom authorization service, and we have a nifty search feature that is basically us fronting Solr. So pretty standard. The requests look like this. We've got a public key we use for authentication. And typically what this thing does, more often than anything else, is it schleps node data back and forth. A node is a server under management. That node data is that full description, attributes, and run list of that server. So the median size we looked at for Hosted Chef, 22K. Top of the third quartile, 44K for these things. So not a huge payload, but also not tiny. We weren't shipping around hundreds of bytes. We were shipping around something more like half 100K quite often. And then we have these fairly expensive authorization checks we do because we actually have role-based access control at a fairly fine level. We've got, can you read these, can you write these, can you delete them or create them on all the objects in the ecosystem. So that can be a bottleneck. We have to check these on every request. And then finally, we've got the set of operations you'd sort of expect. You can create them, you can delete them. They map very easily to RESTful HTTP verbs. So here's the problem statement, amongst others. You look at that sort of support point there, and first of all, there's a huge variability in our response times, lots and lots of wiggle, right? But there's a support point there somewhere around 500 milliseconds, which for a number of our requests is really kind of abysmal. I mean, you could see it for larger requests, but just not fast, not happy with it. So that's me on most. Yes?
Question.
Is that you too?
It's good. You mentioned the JRuby. I'm guessing you tried to run your existing software on JRuby, and why was it just...
Right. So the question is, why not JRuby? Some of these things they were just a matter of when we tried them. We had native, for one thing, we had native extensions at the time that weren't supported. which is a real bummer, right? Because you can get part of the way there. We could probably, having changed the things we've changed now, we could probably run completely there now. Probably would have been a great choice. There was also a bit of momentum. We had been building some other things, like our authorization service was built in Erlang from day one. So we already had an example of a thing that we thought ran well. And so that's, yeah. So pragmatically, it wasn't black and white. We certainly could have ended up there. That's right. So over time, the service looked a little more like this. It was slow in places, highly irregular in ways we couldn't control. And then we had issues with early builds of CouchDB. This is an example of our uptime graph. We run high availability, failover. So the places where there's no data at all are places where we in fact failed over. So this is a view of only one side. But you can see what was happening is that over time, it would run for a while, run for a while, and then we'd either have to restart or it would crash. It was consuming resources, typically file handles, behind us, and getting slower and slower all the time. So part of our dilemma was our data store was in fact the bottleneck for a number of things that we did. And we found out during the course of inspection there were some really good reasons. So you can see the way the graph, yes?
Why is it so much better towards the end?
Yeah, that's what I was getting to. That's a fabulous question. So yeah, why does it get better toward the end? This is a horrible thing to admit. We had a cron script that just restarted it. Yeah, I'm so glad somebody played the straight man for me on that, because that's all. So there you go, heavy on system resources. The other thing we were looking at is, so how much RAM should this entire running system, all the request handlers and the data store and everything, how much RAM should it actually use? Because if you're running a hosted service, obviously you don't want all of the resources consumed to scale with the number of customers that you're adding, or sooner or later you at least don't want some sort of multiple, right? You don't want this to scale out of control. So we looked at it. So we were doing at the time about 60 requests a second, which is not huge. 44K at the third quartile for payload. So that's roughly, just totally non-scientific. This is 2.7 megs of actual active data being schlepped around, right? And obviously there's all sorts of space for code that's running in all of the Ruby interpreters, all sorts of other copying going on, both from kernel to user space, multiple user space copies, a lot of things you don't directly control. So let's just put a multiplier on it. Again, not scientific. Let's say it actually takes 27 megs as far as the data and its copies are concerned. And then we'll figure out how much space the code takes, right? So 27 megs. Nope. So each of our Ruby, Merb, Unicorn workers was consuming 100 megs of RAM at rest after startup. And these days, RAM's cheap, machines are cheap, but 100 megs for a worker that's not actually doing any work yet. And what's the concurrency? It's one request per worker. So you're consuming 100 megs every time somebody makes a call at least, right? That's the way Unicorn works. You read the outside of the tin and it says, should be used for fast requests. Don't worry about concurrency, we got you covered. You've got one process and one request. Super easy to understand. It's actually a great model for a number of things because you don't have any threading concerns, right? And to be kind to Matt's Ruby interpreter, threading's not a thing you really want to approach lightly, right? So this is a good model. Except, under load, 204 megs of RAM consumed for each of the workers. 12 workers per server, 8 servers. What's the magic total? Dun, 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 dun. 19.2 gigs of RAM consumed just to, there we go, schlep some JSON in and out of a database. I mean, it just hurts, right? I mean, RAM's fairly cheap, but seriously, nearly 20 gigs to move JSON back and forth, we're doing it wrong. Doesn't mean they're necessarily bad components, we're doing it wrong. So, what's the moral of the story? Unicorns eat RAM. Solution? I had to do, right, that's the pitch, right? We moved over to Erlang. This is a web service, so we're using Webmachine from the fine folks at Basho. See them everywhere. Any Basho folks in the room? That's out. Yes, of course. Amongst other things, actually, there's a couple of plugs in here. So Webmachine is basically a state machine for HTTP. Super cool in that thing that you see over here on the right, that's what you get if you enable tracing. you actually get these images spit out of where your request goes, what it went through to get there, and what the result was, which for debugging is glamorous, right? It's a view that we didn't have before, A, and it's also just a good framework. So we made this switch. How did we do? The Erlang processes as an aggregate at idle, each worker at idle, 19 megs. Loaded, 75 megs. So under load, we're consuming 600 megs of RAM total across the system running the Erlang servers, when we had nearly 20 gigs running the Ruby ones. Again, I'm not necessarily faulting Ruby, but boy, were we doing it wrong. This is so much better. It was, we made a bet when we started writing in Erlang, because like I said, we could have done it in JRuby or something else. That paid off. That was a huge difference. So we win. Yay. But wait, we weren't done right there. We looked at what Ruby was doing. Some of this was research to tell us we were going in the right direction. Where was the Ruby version of this spending its time? Was it in the database? Because, you know, Couch was not helping us at the time. Turns out it wasn't so much in the database. JSON parsing is slow in every language, right? Turns out it wasn't in JSON parsing either. Was it in crypto? Because we do a bunch of key stuff, and it's kind of CPU unfriendly. It wasn't in crypto. Garbage collection? Garbage collection. We spent 40% of the CPU in garbage collection. We were abusing the interpreter in the pattern that we had. We spent 40% of the time in garbage collection. So, you know, like I said, clearly we were doing it wrong. I'm not faulting anybody else's code, but when you see that happen, you're like, got to be a better way to do it, right? This was CPU usage sort of before and after. So you can see not only was it variable and higher, it goes down and it goes flat. One of the other things that we got out of this is we can now characterize how the system works. Even under load, system works the same way all the time. We've got a very, very, very large customer in testing right now who had the original version and then progressively got these versions as we rewrote pieces in Erlang. And my favorite piece of feedback was, wow, our front ends now are doing so little, you ought to figure out what else you can run on them. It's like they basically got all their resources back, right? So we shed a little tear because we also, in the process of this, moved from CouchDB to a relational database. And there's a bit of a discussion about that. So why did we start on Couch? Again, it's these pragmatic choices. Super easy to approach in the beginning. It's, you know, it's JSON documents behind a RESTful interface, right? Who doesn't want that? It's so easy to get started on. So we're doing frequent gets and puts of node JSON, all this node data. And frequent compaction. Because how many of you have used CouchDB? Okay, so it's append only, MVCC, so every time you write, you're actually appending to the file. And it gets bigger and bigger. And at some point from outside the system, you have to tell it go compact now. And this is true both for the main database files where your data is, but also their equivalent of computed views that do the same thing. So you got to think about if you're doing read, like I said, for our node objects where reads and writes are roughly the same frequency, symmetric, you're writing a lot of the time. You end up spending time compacting. Early builds we were running on, no concurrency accessing a single database. So you have to decide, what's your model? How many databases? If you have thousands of customers, you're not putting them in the same database because now your concurrency goes to 1 again. Do you split them up one database per customer and have thousands of databases? And this, by the way, got fixed, to be fair. We went the thousands of databases route. It's really easy to isolate customers if every one of them has a separate database. Also a little bit better on the security front because it's really hard then to commit to somebody else's database, right? It's the equivalent of doing cross-database joins. Turned out, wasn't that reliable for thousands of databases. So we thought we'd solved one problem, but we played whack-a-mole and that we created another one. And you can't, with the builds we were using, you could not, in fact, ask it to run off and do compaction across those databases on its own. We had to do some stuff internally to sort of statistically decide which ones needed compaction, compact only those. And as you can imagine, right, in the face of this, it was leaking file handles as it was doing so. So that's one of the reasons why you'd see it run for a while and then we'd have to restart it. At some point, we would simply run out of file handles. It had a bunch open just in normal operation. and then we would start performing these games, and it would take off again, and we had to restart. So it became an operations thing. If you got paged in the middle of the night, the first place you started was with the database, which sucks, right? Especially if it's happening multiple times a week. At some point, somebody says, can we get rid of it? And I'm not trying to bag on the Couch guys, but it's horses for courses. It was the wrong thing for us to use in that environment at the time. So what do we actually need there? So we go to replace it. So it needs to be happy with a write level load, because a write heavy load, because we do writes to nodes all the time. Every Chef client run commits a node, at least once. Support for fairly sophisticated queries. It's not just key value. Sometimes we ask slightly more interesting questions. And then it needs a supportable, high availability mode, something that's fairly easy to, both for us to comprehend operationally and then for customers that we sell this to. Perfect. So the obvious question, did you consider the other NoSQL databases? Absolutely we did. As a matter of fact, we were running React for a while, still big fans of React. But we also asked a different question. Can our problem as easily be solved just running SQL? And again, this was a pragmatic choice, because for us internally, if the only thing we were running was hosted Chef, we could pick any technology we wanted and train people up on it. But this is also a thing that we sell to folks. And it's already a bitter pill to swallow if you say, oh, there are all these weird services in here, and this is what you need to know to keep them running. And by the way, we have this weird database technology you don't know, and you don't have guys to run it. It's more load, right? So we measured, right? Which of these actually works? Can we actually use SQL? And again, the fine folks at Basho Bench, super cool tool for this. And it's the nerd kind of tool, because not only can you define your own kinds of web testing, but then you use R to do the analysis. Yeah, I can't say enough about that. Love using R. We're fortunate. We have R guys, Basho does as well. We got R guys at the company. One of our lead developers is an R committer. I would suggest that goes in your hiring profile, because that's cool. So we replaced Couch originally with MySQL, which for what we were doing worked really well. And we didn't have to convince folks that we were selling it to. I hate to hammer on that, but it's one of those things. It made it so easy, especially for customers. This is the thing, especially for customers already using it. You don't have to teach them anything. You got DBAs on staff, right? You got guys who know how to do MySQL replication. Check. And one complaint about your product goes away. Cool thing is, we replaced it underneath while the system was running. So this is the equivalent of what we did. We moved thousands of customers and tens of thousands of node objects while the system was running, and nobody noticed. I love that. By the way, apparently this is a thing. It's like, not just this video. This is a thing that lots and lots of people do now. Not recommended. But I'm gonna spin through some of the rest of this fairly quickly because we're running out of time. But talk just a little bit very quickly about how we did that live migration, because it starts out, you think it's fairly easy and you got a plan, right? You don't want to take down time for the reasons I said earlier. So all these organizations, basically each customer, put them into a read-only mode, copy their data over, change the route. So we have the running service over here in Ruby. We're going to change the route to the running service in Erlang. Nobody's going to notice. That is, in fact, in abstract what we did. Turns out it gets harder. It gets really hard, really fast, right? We wrote this tool that we basically have a dark launch feature flipper. For any of these new features, we can dark launch an organization. No other organizations know about it. Only that one of them is affected. So you have to coordinate that with your load balancer config, right? Or rather your reverse proxy to change these routes. Move batches of orgs around, because if you do them one by one and you start multiplying it out, it's like, how long does that take? Wow, it's a batch operation. Really want to go faster. Tracking the status as you go, and then these things tend to crash in flight. If you drop the pieces on the floor, you need to know how to pick them up as well, right? So you need to track the in-flight requests. You need to be able to drain them off when they're going to the old database before you move over to the new database. Here's a thing nobody really thought of. This feels like a scripting job, right? Yeah, we could have written it in Ruby. Strangely enough, Gen FSM, writing a finite state machine in Erlang, this lent itself very directly. Super cool. It was one of the things we came out the other side realizing it's a pattern we're going to keep applying when we do this, right? You're moving through various states, be it success or failure, and having to decide what happens in that state. First of all, you look at the problem and it looks like a state machine, and then you solve it with a state machine. Plus you get a free REPL. All right, so flip through here fairly quickly. But of course, yeah, you know the quote, right? No plan survives first contact with the enemy. Yeah. I won't go through all the details here, but the CouchDB CPU usage, and then MySQL. By the way, that's actually MySQL. Yeah. I think it actually might be there we go. Same graphs. Yeah. Both the variability and just a lower load average, right? And then my favorite here. I talked about the wiggle before, API average latency. The wiggle went away and the average dropped dramatically. So under load, we're seeing these front-end services written in Erlang perform the same way. Like I said, you can characterize the system, you know what it's going to do, even as concurrency goes up. Same thing here, right? The 90th percentile latency per endpoint. One of these, oh yeah, this is the, in terms of memory, this is the interesting one. Red up here, that's swap. That was diving into swap. And the moment your service dives into swap, you're done. It just basically stops responding. There's no swap here. Write requests, this basically says it dropped dramatically because almost all our traffic is node traffic. First thing we moved was nodes. We running out, oh, see now every time hash moves, I'm and then finally, same thing, network traffic decreased dramatically for two reasons. The most important of which actually is we learned a lesson here and we started gzipping our content. Super simple thing, it's low-hanging fruit, right? So now when we move these nodes back and forth.
How is this related?
Oh yeah, so it's funny. It's not actually a separate product. We do a really poor job explaining it. Chef Solo is the convergence engine, basically just not talking to the server. Yeah. So it will work with when I said the server is a publishing platform, it's all about being able to upload versions of cookbooks, track versioning, download them to the proper places. If you subtract that publishing portion and you say, I'll copy the cookbooks around myself and I'm not as concerned about versioning, then once the cookbook's on the file system, it's Chef Solo, it's just a convergence engine. And some folks choose to do it that way because they've already got some sort of background way to share out files, or they've got some sort of shared file system across their infrastructure, and they don't want an additional server in the mix. Cool.
On the server side of things, when you guys switched from Ruby to Erlang, you talked about the memory savings and so on. What about other stuff, CPU?
Everything. I sort of glossed over the CPU graphs. Everything went down. I can't tell you right now exactly, because I don't have current data, exactly how many cores we have devoted to all of the Erlang endpoints. Because when we did this, these slides are a bit dated now. When we did the original analysis, this was right after having moved basically the heaviest endpoints. We started with nodes because it's the most data, search because it's fairly highly trafficked, and then after that I think we did rules. So I don't know what the totals come out to, but in each of those cases, a lot less CPU consumed. And then just the concurrency, not having to pin process to request singular with the other thing I didn't touch on directly is part of the reason that there's so much RAM usage is that you would like copy on write semantics. And we use Ruby Enterprise Edition, which has the copy on write patches, except that the way all of this churn goes and other artifacts of the way we load things, everything gets touched a lot. And when it gets touched, you don't get copy on write, everybody gets their own. And so we basically defeated the system, what we were doing. So we really didn't get any choice, there was no savings.
So would you say now, having gone through all this, that Erlang and MySQL or some relational database was actually the best choices you could make at the time? Would you do anything differently?
I would say yes, they were the best choices at the time, given the other concerns. I wouldn't necessarily say that a relational database is the closest map to what we do, but it is certainly the easiest thing to explain to our external customers. If we only ran this as a service, a hosted service on our own, it's not as clear. I mean, Erlang, yes. The relational database is not as clear. And one of the things, so we were using React for a while, and we were a little too early on, and the search wasn't quite what we wanted at the time, and I think it was before secondary indices. So that's a viable candidate now, especially.
Say something about 60 requests per second and how many requests per second you are setting now?
That's a good question. Like I said, this is fairly dated. I don't actually know. I'll find out. It's a really good question. I want to say that it's probably somewhere just around Delta back now. This is fairly dated. All right.
Cool. How long was the migrations were like? How long did it take?
Oh, yeah, and that's a good point. I didn't touch on that. We figured it would take about 3 hours. It took 3 days.
Sorry, I mean the development time.
Gosh, I just outed myself, didn't I? The development time, for all told, the entire port of all of the API endpoints. I mean, we had other work going on at the time, but it took us nearly a year. We are just now finishing. And a lot of that is that we built a really interesting test framework while we were doing the port. Because the thing that we realized is we needed fidelity with the existing server. And we built up this testing framework that we then pointed at both as we were doing the port, which was really cool. So I would say even 30% of the time we spent in total was probably testing. And that's all from the developers. It wasn't a separate team. Yep.
What did you find most difficult in converting?
There were cases where we knew what we wanted the outcome of the request to be, but mapping that to two things, both mapping that to Webmachine in its fairly strict intent was difficult. There are points where you just sort of want to bail, and you can, but it's not exactly obvious that that's what you want to do. And there are other cases where you're working your way through the request pipeline and you realize that you're going to gather some data here that's actually not useful until over here. So you have to put it somewhere and memoize it until you actually use it. So that mental mapping from the way we had done it in Ruby to the way Webmachine expected us to do it, that part was difficult. The other part that, I don't know if I'd call it difficult, but it was the thing we decided to spend some time on, was a way to do much better code sharing across resource implementations. We played some games originally with parse transforms and went away from that, but we ended up with a thing where now we can share both quite a bit of the standard resource implementation and actually standard record handling. We have sort of a default set of fields in a record that we then sort of expand depending on which API endpoint it is. So it was all down to that conceptual mapping. How do you best use this tool rather than the way you were thinking about it before?
What about lines of code in Ruby?
That's a great question. I don't know. That's another one I should find out. It goes somewhere. Because I couldn't necessarily say from that standpoint there's a clear win, because in both cases we lean so heavily on the frameworks beneath us. So I'm not sure how easy a comparison is. Cool. All right.